Okay, let's get started. Good morning and good afternoon, everyone. Welcome to today's Easy5 2015 release webinar. My name is Ejin, and I'm the Product Marketing Manager for Atoms and Easy5 at MSC Software. So today's presenters will be Dan and Claude. So they are both our senior development engineers, and they have many years of experience with the product, with Easy5, as well as working with the customers in different industries from heavy equipment, aerospace to automotive. In today's webinar, Dan and Claude will give you a brief overview of what is Easy5 to those who are not familiar with this product, and then we're going to talk about some of the new features that we have introduced in the 2015 release, which has already been released a few weeks ago. At the end of today's webinar, there will be a Q&A session. So if you have any question for Easy5, the product, or the presentation, please type the questions down in the Q&A window. So we will try to get them answered either during the Q&A session or following the event. Okay, now I'm going to pass the presenter to Dan.
Hello everyone, thank you for tuning in this morning or this afternoon, wherever you are. I'll start with the Easy5 overview. For the benefit of those who may be brand new to Easy5 or never used it before. Easy5 is a collection of software tools for system-level simulation and analysis. It is a block diagram and connection methodology. The physical equations for the mathematical model are encapsulated by components that are represented by icons. The component icons in a schematic are related by connection lines, the connection lines representing the data flows between the components. The components, along with the connections and the data that you provide, constitute a system-level math model. The inputs to an Easy5 model would include parameter values such as orifice diameters or pipe lengths, physical properties, correlations of such things as friction factors, tabular correlations for complex geometries, such as tabular correlations of flow versus pressure drop, and other types of parameter values. It also includes initial conditions and boundary conditions, component connectivity, and then after the model topology has been defined, one needs to define the analysis type, be it transient simulation or steady-state analysis or some sort of linear analysis. And then the outputs that are requested from that analysis. The outputs depend upon the type of system being modeled and what type of analysis is performed. But for a typical transient nonlinear simulation, you would be getting plots of time-varying system parameters such as pressures in the system, temperatures, flows, displacements, velocities, and heat transfer. Easy5 has been developed continuously for the past 40 years now. It originated at Boeing and in 1986 was commercialized with the first graphical user interface. In 2002, it was purchased from Boeing by MSC Software, and development has continued to the present time. Easy5 models can be simple models from a single discipline, or they can be complex models from multiple disciplines. Here's a list of some of the types of physics that can be modeled with Easy5. Today we'll be focusing on hydraulics and electric power systems. Now, if an engineer has a detailed understanding of the equations governing the system that they want to model, they can use primitive mathematical components from the general purpose library to build a low-level model. In this example, we have a spring mass damper system. Here are the equations that one could formulate for that. And then using general purpose library primitives, you can formulate these equations. Each of the blocks in this schematic diagram represent one of the mathematical operations in this set of equations. You can also formulate an Easy5 model using what we call higher level components or system level components. It's the same physics, same block, same free body diagram, but now we're capturing that in a single library component. In this case, the user would not need to know the detailed equations that went into this model. They simply need to know the parameters, the mass, the spring constant, the damping or friction parameters, and from that, a model can be built and analyses performed. Another example, we have a hydraulic actuator and a rack and pinion. Each of these are represented by a single Easy5 component, one for the hydraulic actuator and one for the rack and pinion. The connection lines represent the data flows between the two components. Together they constitute a system level model of the hydraulically actuated rack and pinion. The user just needs to have some reasonable design parameters, or at least reasonable estimates of those design parameters, such as bore and stroke for the hydraulic actuator, gear ratio for the rack and pinion. Now going back to the situation where for a component you know the detailed physics and the detailed equations that go into constituting that math model, a user can use either Fortran or C and formulate their own code block. We call that a user code block that can be incorporated into the system level math model. So in this example, we have some inputs, a state, and a couple of variables and some equations. These inputs and variables can then be connected into the model. Easy5 has a number of predefined application libraries which are commercially available. Of course, I've already mentioned the general purpose library, which comes with Easy5. There are also a number of application libraries that are supplied by MSC. Some of these are separately licensed. These include the thermal hydraulics library, gas dynamics library for modeling pneumatics and environmental control systems, the multi-phase fluid library for modeling cryogenics and refrigeration cycles, the aerospace vehicle library, and the new electrical systems library, which Todd will be discussing shortly. There are also commercial third-party libraries from Ricardo, powertrain library, the fuel cell library, and the system internal combustion engine library. Now, Easy5 users can use the same methodologies that Claude and I use for developing the commercial libraries. You can use those same tools for creating your own libraries for in-house or in-company encapsulation and reuse. For example, GE has a number of custom libraries which are used throughout the world within their company for modeling gas turbine systems and power generation systems. Now, that's a brief overview of Easy5, and now we'll talk about the enhancements for Easy5 2015. I'll talk about functional mockup interface and the 64-bit GUIs and then turn it over to Claude. Functional mockup interface is a protocol for interfacing software tools from different disciplines and often from different vendors. There's a website that you can go to read about it, or you could just Google functional mockup interface and get several different possible sources of information for this. Functional mockup interface, or FMI, has a master program which incorporates or communicates with slaves, which are called functional mockup units. The functional mockup units, if they're connected to each other, can also communicate with each other. Easy5 can export a slave FMU representation of an Easy5 model, or it can import one or more slave FMUs into an Easy5 model, in which case the Easy5 model becomes the FMI master. The FMI specification supports two different modes. One is co-simulation, where each FMU solves or integrates its own equations. That's what Easy5 2015 is supporting. There is also a second mode called model exchange, where the master becomes the solver for the slave FMUs. That is in work for Easy5 and will be supported in a release in the near future. For those of you who've ever exported a Simulink S function or a DLL from Easy5, the process of exporting a slave FMU from Easy5 is very similar. It requires a library license feature from the external interface library. There is a new component in the external interface library, or I'll call that from here on out the XI library. This component FM represents the connections and interface to the FMI master. So if you have an Easy5 model that you want to convert into an FMU, you add this component to your model, make the connections to and from the model, to and from the FM component. Connections from the FM component represent data that flows from the FMI master to the FMU. And conversely, connections to the FM component represent data flows from the FMU to the FMI master. Once this component is connected, you simply go to the Easy5 build menu, select export model as, and there's a couple of new items in the submenu for exporting models. Detailed instructions are contained in the external interface library user guide. If you would like to import an FMU into Easy5, you do that in a different way. You start from the Easy5 Add Components panel, and from the library list, you select Extensions. And there will be a functional mockup unit icon in the Extensions group. Add this icon, add this component to your model, open the component data table. Now, when you first open this component data table, it will be very generic because you haven't yet specified what FMU you're importing. You do that by clicking on the Select Configure button, and that will walk you through a process for completing the FMU import. And when you're done with that, you will have the additional inputs and additional states and variables which are specific to the FMU. The documentation for FMU import is accessed from the info button in the extension component data table. Next, I'll briefly talk about the 64-bit GUIs, which are available with Easy5 2015. Now, in previous versions of Easy5, even though you could create 64-bit model executables or export 64-bit DLLs from Easy5, the GUI itself was 32-bit. With Easy5 2015, you now have 64-bit GUIs available for Windows 64 and 3 Linux platforms, Red Hat 5.7, Red Hat 6.3, and SUSE 11 Service Pack 2. These are full 64-bit implementations. To take advantage of this, for those of you who have your own in-house libraries that you've developed and are using, you will need to port those libraries from 32 to 64-bit. Just pretty much in the same way that you would need to do if you were porting from, say, Windows to one of the Linux platforms. It's the same sort of process. It takes about 1 minute per library. The instructions for doing that are on page 2 of the 2015 release notes. There's a 64-bit matrix algebra tool which can now be seamlessly started from the Easy5 GUI or spawned from the 64-bit Easy5 GUI. 64-bit EMX files can be seamlessly exported from Easy5 and imported into math. An EMX file is just a DLL representation, a DLL that can be loaded into the matrix algebra tool, and from that you can script analyses or do a number of different types of scripting operations. And an EMX file is, again, just a DLL that can be loaded into math. When you export an EMX from Easy5, then you have a DLL representation of the Easy5 model that can be loaded into math. This gives improved performance for analyses that utilize EMX files. For Easy5 2013, there is still a 32-bit Windows installer available if you need to use that. But we encourage everyone to migrate to 64-bit installers and installations as soon as they can.
Okay, well, I'll begin here. I'll talk briefly just about some improvements that were made to the thermal hydraulics library, and then I'll talk about the new electric systems library. Okay, so there were a few additions made to the hydraulics library in Easy5. The first thing is the addition of acceleration forces to the transient momentum pipes. So this means the acceleration can be added as an arbitrary vector to those pipes. So if you have a situation where your pipes are in a vehicle that's accelerating, this will now be taken into account. Another improvement is an expanded solenoid modeling capability. You can now put in some information for magnetics in a servo system which is actuated by a solenoid. So That's been added. We also have 2 new fluids for aerospace applications, both type 5 phosphate esters, which are Skydrol PE5 and HiJet 5. And also a new configuration was added for the 6-way valve that's in the hydraulics. And I won't talk any more about that because I want to continue on to the electric systems library. This is a new library for Easy5 2015. And it's for modeling electrical systems, not so much electronics in the terms of modeling PC boards or things, but more in terms of modeling large electrical systems or power systems or electromechanical systems or control systems. And the library uses time domain-based models. It's not phase-based at the present time, but that's not available. So it's not so suited for modeling huge grid networks, but it is quite suited for modeling some electrical power systems and getting a lot of detail about the frequency domain, the time domain performance of your systems. And this library replaces the Ricardo Electrical Systems Library, which has not actually been available from MSC for several years. So if anybody's using the Ricardo Electric Systems Library, this could be replaced with the Easy5 library, which has all the functionality that's in there and some extra functionality. So what are some potential modeling uses for this? Well, some uses would be for power switching networks where you have power systems that require switching. You can use it for AC and DC motor actuation, so for control surfaces or robotics, you can use it for that. If you have systems that are coupled with hydraulics or mechanical systems that are powered by electric motors or run generators or have control systems that are designed with electrical controls, that can be also modeled with this library. It also does do electrical grid simulation, and you can do I'll show you an example of that, where you can actually do a fairly detailed analysis of an entire electrical supply network. And it also does an electrical generation. Also, if you're interested in hybrid or electrical vehicle design, a number of the components in the electrical systems library, which I'll show you in a moment, are very well suited for modeling the components in these types of vehicles. So in automotive system, some example applications would be charging or accessory power systems, and you need to control voltage or current, battery systems, and the drive systems also can be modeled in these kinds of vehicles. In aerospace, there are a number of applications, actuation of control surfaces, the analysis of safety margins, and for instance, auxiliary power generation. This picture shows the APU there. For wind energy, you could model a number of the components in a wind energy system, not only the components in the electrical components in the turbine itself, but also the switching and power regulation equipment and the grid and transformers that send the power out. And investigate transients, for instance, during switching events, which are actually quite significant in a number of these systems. So what is in the electrical systems library? And we have a number of machines, DC machines. You have shunt field motors of generators, permanent magnet motors, a brushless DC motor, and commutated machines. And many of these machines are multiple or single phase. You can select what you want. For synchronous machines, we have motors and generators. Induction machines, capacitor start-run motors, and a stepper motor for doing actuation. And those pictures up at those diagrams on the upper right there are actually from our documentation. Then there's a selection of types of transformers and a number of ways to model transmission lines. You can either use lump parameter models or a three-phase distributed parameter line. So you can get whatever accuracy traded off with simulation speed that you want. And there's a number of passive components for loads and some voltage sources such as a battery and then a fixed AC source if you don't want to go through modeling generation or the battery. As far as electrical control, there are a number of components available. One of these are circuit breakers and simple switches. We have mechanical coupling aids as a convenience in the library. So we have a way to convert rotary to linear motion. There's a drive shaft in there, an inertia, a gearbox, and a clutch. This is actually a triple S clutch that you're looking at in next to the right there, and that is substantially modeled. You can model that with the clutch component. As far as electronics, there's a good selection of general purpose components for modeling electronics. We have pulse width modulator inverters for changing AC to DC current, rectifiers or DC to AC. There's a sine or triangle pulse width modulator inverters. There are stepper motors, controllers, DC to DC switch mode converters like buck or buck boost, SCRs, and GTOs, and H-bridge driver for motors. And there's a number of primitive components for modeling electronics that include diodes, a thyristor, inductor, a capacitor, a resistor, and if I get a chance, I'll show you some of those. Okay, so now what I'm going to do is do a short demo, and I'm going to bring up Easy5 here. Okay, so let's see. So I don't know how many of you have seen Easy5, but I'm actually going to build a small model and show you how you can go about doing that. So here are the components available, and this is the electrical systems library. There are a number of components available in Easy5, libraries available in Easy5 here. I'm using the electrical systems library, and I'm just going to drag in this component here, which is just the global properties, which just tells me what unit system I'm using. Okay, so what I'm going to do is I'm going to build a rectifier, and you can see this. Here's a picture, just a picture of a full wave rectifier, and see if we can build this up in Easy5 and get some data out of it. Okay, so first of all, we're going to need some diodes. So I'm going to go here and I'm going to go to the basic circuit elements, and I'm going to pick a couple of diodes. Okay, and to get them to look like the picture, I'm going to turn them around. Let's go that way. That. We'll turn them around like that. And then I'm going to need a couple of capacitors, filter capacitors for each side. So I'm going to put one here, and I'm going to put one here. Okay. And then I'm going to need a load, so I need the resistor. Here's a resistor. I'll put the resistor here and turn it around so we can get it to look like the picture. Okay, so now let's see if I can connect the electrical signals from the diode to the capacitor. What I'm going to do is select this terminal here. Oops, I'm sorry. I'm going to select this terminal here and connect it to here. And the menu that I see shows me I have some choices about, on the diode, which side I want to connect to this capacitor. So since it's not really clear which side I would like to connect. So I want to connect this terminal. And the connection is now made, and you'll see the line draw like that. Even though this says this is called the negative terminal, it is where positive current flow, positive voltage will appear, as that's a convention with a diode. Okay, now I've connected the capacitor there, and I'm going to connect that, the positive voltage, to the load. So I'll connect this to here, and again, it doesn't know which side of the resistor I'd like to connect, so I'm just going to connect it to the inlet of the resistor. Then I will connect the outlet of the resistor to the capacitor here. I'm going to move that here. Let's move these so they look a little nicer. There. Okay, and then I'm going to connect this capacitor there. Okay, now I have more or less the complete circuit. And in order to join these together to make a junction, I'm going to add a junction component in here. And I'm going to connect this part of the junction to there, and it's going to ask me which part of the junction I want to connect. Okay, and then here I will connect down to here. And there was no choice there because there was only one place left on the junction. That's that part. And now I need to add a voltage source. So I'm going to go back to my miscellaneous group, and here's a voltage source that I can use. And I'm going to connect the voltage source into the junction. Whoops. That's because that didn't connect, because the voltage source, unlike all of these other components, is three-phase by default. So we're going to change that down here to single phase. Now it's a single-phase voltage source. Now it will connect. There we go. So I haven't put any parameters into this model, but it doesn't really need any. The diodes really don't need any parameters. The capacitors do. Let's put in a nice big capacitance into these capacitors. So here are the inputs, and the capacitance is in farads. So I'm going to put in 0.01, which is actually 10,000 microfarads. And we'll do that with this one too. Right. And then let's put in 50 ohms, say, for this resistor. Okay, and if I just check the voltage source, it's set by default to 110 volts, 60 cycles. Sorry for all you in Europe, but you can change this. All right, so what I'm going to do now is create the executable, which what it's doing is it's translating all of these components into their mathematical equivalents into computer language, which is Fortran in this case, compiling and linking that into a program which will now run. So all we have to do is say what we want to look at. So here I'm going to look at the simulation form on this side. Here. So I'm going to run this to 1 second. And I'm going to look at, make it a little more detailed so our sine waves look nice. Now, you can, at this point, I could just run the simulation and I could just plot everything and then just look at all the results. But it's kind of nice to set your plots up beforehand if you only want to look at a few things. So that's what I'm going to do. I'm going to select a couple of outputs. So I'm going to look at the capacitor outputs here. Let's look at the capacitor output there. And then I'm going to look at the load voltage, which is coming out of the source here. And I'm going to ask that to be overplotted. Okay. Now let's just take a look at what we get. So if we run the simulation. Simulation is completed. I'll move the plots over here. Here are the plots that we just got. So we can take a, zoom in here. Let's just zoom in on a bit of this and take a look. Okay, so here it looks kind of what you would expect. The positive voltage is here. It's rectified fairly well, and the negative voltage is down here, rectified fairly well, and the red in between is the load voltage. So that's an example of how you would build a simple, very simple model in Easy5. Let's take a look at something that's a little more complex. Okay, let's get this so you can see it. Okay, so this is built with the Electrical Systems Library, and this is a complete power system. Here I've got the compressor and turbine model, and if you look inside here, I've got I've made some customized components which are just Fortran code, which I coded up, but you can also use components out of another library, the Gas Dynamics library in Easy5, if you wanted a more detailed model. And I have a controller here that I've made on the turbine so that I can control the speed of the turbine by controlling the combustion heat. Okay, and then it runs through the drive shaft runs through a clutch and that drives the generator. There's a delta Y step-up transformer here, and it's going to run at about roughly 100 kilovolts. That's going to run through a 100,000 meter high voltage line, stepped back down, and then through a low voltage distribution line, and then that's going to go out to the consumer load, which is out here. Now, what I've done in the simulation is I put in an emergency breaker here. And you can't just, of course, in the power system, you can't just open a breaker because you'll destroy half the system. And so you've got to provide some kind of alternative emergency load if you want to actually open the system to dump the current. So this breaker component, I'm going to look inside of it. It's actually there's some current sensing electronics here that's built with the general purpose library in Easy5 that is available with every copy of Easy5. And I've got that to run this to a, and this will trip the circuit breaker when the current goes over 500 amps in the main line. And what it will do is open the main circuit breaker, and it will shut this other breaker here, giving us an alternate path to a load where we can dump the current and prevent the disastrous transients in the system. Okay, and this takes about 3 or 4 minutes to simulate. So we're not going to have time to do that here, but I can show you, I just did that just right before this presentation, and I can show you some of the results here. So we're looking at the load voltage, and at a little after 4 seconds, what happens is I've created a situation in the model where there's a short circuit. So what happens is the load power, C, goes down to 0. The dump power comes up because the circuit breaker is closing there for the dump load. You can see the load voltage and the current are shutting down in the main line. And you can look at, I've got a number of things we can look at. We can look at shaft torque and what's going on in the compressor and the turbine here. And I can see, for instance, if I look at the turbine speed during the transient, there's a slight, the angular speed, there's a slight change, but it's fairly well controlled. If I didn't have that emergency breaker in there, you would see something a lot worse because the control system might not be able to handle adjusting the speed for this system. And I can look at the high voltage here, check at all times the generator is producing roughly the same high voltage here, and it's producing about 2300 some kilowatts. And then down here, though, the power, even though the speed is regulated fairly well, as you can see down here, I can, so this is a really good way to examine in detail what happens in a system like this. Yeah, so that would conclude the presentation.
Okay, thank you, Claude. So I'm going to take the control back at this point.